Alright guys, we have another question from the second chapter of the Mechanics of Materials by Beer and Johnson, and we have question 39 that there are two cylindrical rods AC made of aluminum and CD made of steel. They're joined at C and restrained by the rigid supports at A and D for the loading shown, knowing that the elastic modulus for the aluminum is 10.4 times 10 to the 6 psi, and the steel has 29 times 10 to the 6 psi. We need to determine in the A part the reactions at A and D, and B part deflection of the point C. So looking at this, first of all, we're going to draw the free body diagram. Since we don't have any force in Y direction, we're going to consider only X forces in X direction for now. I'm drawing the free body diagram for this part. As we can see, the two forces in B and C are trying to push the rods to the right side. So the right side, or the reaction that we have at D, trying to go against that force. So we can call this one RD, and on the left side, the reaction would be in the left direction, RA, because the wall is trying to push the rod back. So these are the correct directions, and if we just do sum of all forces in X equals 0, this is our X direction. We basically have 18 plus 14 minus RA minus RD is equal to 0 because of our equilibrium condition. Nothing is moving in here, we're on a static condition, so RA plus RD is 18 plus 14, which is going to be 32 kips. So the main equation that we have in here, we're going to use our deformation equations, and what we're going to see in here is that at the end of this, the deformation of the AD is going to be 0 because it's fixed at two ends, and we know that this AD consists of the deformation of the part AB plus part BC plus part CD. So we'll break it down into these three, and the reason for these different sections is that wherever we see a force is applying along this rod, that means there's going to be a change in that rod. So we're going to start with doing our sections along different parts of this rod. So we're moving from A to the right. So first of all, we're going to do a section right before B just to figure out what's the force in every single point of this rod. Very similar to what we had in statics. So basically, when we were trying to find the internal forces, this is exactly what we were doing, but obviously there is no shear stress because there is no Y force in here, so we only have axial force. So we're gonna move on with from A to B, and that's gonna be our free body diagram. That's our section. We have RA to the left, and the other force we can call it P. And based on this, we can find our force. We're going to do again sum of all forces in X equals 0. From here we have P minus RA is equal to 0. So the force P is equal to RA. And our deformation for AB would be P times L over AE, or basically RA times the length. Again, our cut is right before the point B, so we're not considering the 18 kips in this free body diagram, but for the next one, we're going to consider that. So the length is 8 inches, so 8 over the area. We have the diameter for the rod, so pi divided by 4 times the area. We have 1 and 1/8, so 9 divided by 8 squared. That's going to give us the area, and the elastic modulus would be the elastic modulus of the aluminum, which is 10.4 times 10 to the 6 psi, or pound per inch squared. Keep in mind that our force in here is going to be in kips since we have all other forces in kips. So we're going to do 10 to the 3 in here, and that's going to give us delta AB based on RA. You can just calculate the coefficient in here very quick. So 8,000 divided by pi divided by 4 times 9 divided by 8 squared times 10.4 times 10 to the 6. So that's going to be 7773. Let's do 2 digits, 86 10 to the minus 6. And we're going to move on to our second section from B to C. This is going to be our new section, so we're going to go right before C, and we're going to have force 18 kips in here, same RA, and we can consider this new force P. So this time if you want to find the P, we're going to have P plus 18 minus RA is equal to 0, or our P is RA minus 18. So delta BC would be, again, PL over AE. So RA minus 18 times L. Now we're looking for the distance from B to C. So this length, don't get confused by the whole length, because that would be deformation for that part, and also the force will be that part too. So B to C is 10 inches, and we're going to multiply by 1,000 just to do the unit conversion. Pi divided by 4, same diameter, 9/8 squared, and also same elastic modulus, 10.4. So let's see what we get in here. So RA minus 18 rest. So here we just have 10k pi divided by 4, and the rest is the same. So this is going to be 967.3210 to the minus 6. That's our BC, and the last one would moving from C to D. So RA, we have the 18 kips here. We have 14 kips in here. And that's going to be our force P. Again, we need to find the force P. Sum of all forces in X equals 0. So P plus 14, 18, 32 minus RA is equal to 0. So P will be RA minus 32. So delta CD, RA minus 32 times the length of C to D, which is, again, 10 inches. The diameter is also different. So 10 to the 3 to get the force in pounds. Pi divided by 4. Let's see, what's the diameter? The diameter is 1 and a 5 at 8, so 8 plus 5, 13/8 squared times the elastic modulus was 29 times 10 to the 6, and RA minus 32. Let's see what we get in here. I'm going to keep that as is. This is 13 divided by 8, and this is 29. So 166.27 10 to the minus 6. And we have each of these based on RA. So we have delta AB, delta BC, and delta CD. And again, we know all of this. Delta AB plus delta BC plus delta CD is equal to 0, because the two ends are restricted. So we're going to end up with one equation in here, and we should be able to find the RA. And if we calculate that, our RA would be 1907.45. Oh, sorry. So what we're going to get is that, let me just show the coefficient just to double check your answers. 1907.45 RA is equal to 22. So from here we can find RA, which will be 22732.4 divided by 1907.45. So the RA would be 11.92 kips. So now that we have the RA, if we get back to our main equation at the beginning for the free body diagram of the hole here, so we found our RA is 11.918 here, so we can find RD. So RD, or the reaction at D, will be 20.082 kips. So that's going to be the answer for the A part. And for the B part, we need to find the deflection of point C. So deflection of point C would be basically delta AB plus delta BC. And now that we have RA, we just have to put our RA in here. We can find the AB, and also we'll put our RA in here. One thing that if we look at in our BC is that it was 11.918, and we're going to get a negative value, and this negative value that shows that the BC part is actually shortened. And for the AB, we can see that it's elongated, so we don't get any negative values. So AB is actually getting longer. For this amount of value, just have to again put 11.918. So let's see what we get. So basically 773.86 times 11.918 plus here we have 11.918 minus 18 times 967.32. So this value here would be 3339.62. We have a 10 to the minus 6 inches, or it can be written as 3.3396, 10 to the minus 3 inches. And that shows that the point C is deflecting to the right this amount. We can also go with the BC part. Since our main equation was delta AB plus delta BC plus delta CD is equal 0, if you just bring this one to the other side, we can see that deflection of C is also equal to this value. So we are moving a little bit to the right for the point C. And yeah, that's pretty much everything for this question. Everything was clear. Let me know if you guys have any question. You guys take care. I'll see you in the next video. Have a good one.